Thank you very much. It's a great honor and pleasure to be here today and speak to you about tipping points in ice sheets on Greenland and Antarctica, as well as the potential of tipping points in society. And I want to start off by reminding all of us of what a special time period we actually live in right now. We learned yesterday from Andy Watson that if we compare the entire history of Earth to a year, then what we're really looking at when we think about the human history, and it's really just the last few seconds of that entire year. And well, a lot happened in those last few seconds. What you can see here is the temperature evolution since the last glacial maximum to today. And for me, at least, there are two really striking things here. One is that the last thousands of years in the Holocene, during which our modern human civilizations have actually developed, we've actually been living in a very stable climate. And the second thing is that the difference between an ice age, so this is the last glacial maximum roughly 20,000 years ago, and today, that's about 3 to 4 degrees of temperature difference. And that doesn't sound like much, but it's really easy to imagine that if 3 to 4 degrees makes the difference between an ice age and an interglacial as we have it today, then we can also imagine that 3 to 4 degrees of warming would really lead us into an entirely different world. And the next thing that you can see here is that the very recent past, this is almost like a vertical line, the human influence on the global temperature evolution. And what we're facing in the near future, well, these are the 4 IPCC climate scenarios ranging from the RCP 2.6, which is still in accordance with the Paris Climate Agreement, so staying below 2 degrees of global warming. And in contrast to this, we here see the RCP 8.5, so our business as usual scenario, which could really lead us to warming that is not only much larger than the difference between an ice age and an interglacial, but also would happen on much, much faster timescales. So I really think it's fair to say that humans have become a geological force and that we really have entered the Anthropocene. Now, why do we care about ice sheets on Earth? Well, first of all, they're a wonderful climate archive. They store in them the history of Earth's climate for the past hundreds of thousands of years. Secondly, they are also the largest sea level contributor in the future. So the overall sea level potential from Greenland and Antarctica, that's more than 65 meters. And 7 of those meters are currently stored in the Greenland ice sheet, whereas 58 meters of sea level potential, that's what's stored in the Antarctic ice sheet. And so I think it's really important that all of us actually care about the ice sheets here on Earth. And in German, we have this expression of the eternal ice. In German, it's das ewige Eis. And I remember when I was in Antarctica for the first time, I was looking at this almost steep wall of ice standing in front of an ice shelf on board of a research vessel. And I was thinking, well, maybe this expression is actually true. This does seem like it's not moving very much, like it could be the eternal ice. But of course, in fact, we know that that's not at all true, but ice is constantly moving. Even in equilibrium, which is what we see here, ice is constantly moving. You can imagine these little white dots as snowflakes that you distribute over the Antarctic ice sheet. And as you can see, we have very different behavior in the interior of the ice, where velocities are very close to 0, so just a few centimeters of ice flow per year. Whereas once we go to the ice shelves and ice streams, it actually becomes much, much faster. We enter a different flow regime. And the ice shelves actually move at a pace of several kilometers per year or several meters per day. So I could really stand on an ice shelf here in the morning, and then tonight I would be somewhere over there. So for ice, that's actually really fast flow. And this is just an equilibrium. So the mass balance of ice sheets is really determined by these processes. You have accumulation of snow at the surface, which is then condensed into ice, and then it flows due to its own weight, due to gravity, it flows in direction of the margins into the ocean. And there's this very special point, basically a triple point between ice, ground, and ocean, which is the so-called grounding line. And this is where the ice becomes thin enough that it can become afloat and form these floating tanks, these ice shelves. And this is particularly the case in Antarctica. What makes it so difficult to understand and also project ice dynamics, those are all the feedbacks that have to do with the ice dynamics themselves, but also feedbacks between ice and atmosphere and ice and the ocean. And here you just see 4 potential positive feedbacks that are associated with ice dynamics. And you can imagine that this really leads to highly nonlinear dynamics, and therefore it's a very complex issue and very difficult to project sea level rise from Greenland and Antarctica. And I want to go into a little more detail concerning 2 of these feedbacks. One has to do mainly with Greenland. If you followed the news in the past couple of days, you've seen that another heat wave has actually reached the Greenland ice sheet just now, and maximum temperatures are currently above 20 degrees Celsius. So that's really an extreme year. And this comes just after an already extreme year with respect to melting in June. So this is a graph here from The Economist showing the June melt area in comparison to the median of the past decades. And you can really see that the melt area here was way out of the 80% range that is sort of typical for the Greenland ice sheet during June. And now again, in July, we're facing very high temperatures, so we'll see what this looks like for this month. Now, the question is, how does this extreme temperature, how does this extreme melt, how does it impact the Greenland mass balance and also the overall stability of the ice sheet? And there is actually a positive feedback mechanism associated with melting at the ice sheet surface. And this mechanism is something that we all know from mountain climbing. So if you hike up a mountain, you know that temperature drops. And of course, the reverse is also true. And that means for the Greenland ice sheet, if you have enough melt and you actually lower the ice surface enough, then you reach higher temperatures at the surface just due to this lapse rate, due to this elevation feedback. And that again means that you have, with higher temperatures, you have more potential for surface melting. So you might lower the surface once more, again, higher temperatures, more melting, and so on and so on. So that means there can actually be a critical temperature associated with a critical elevation at which there is no other solution to this issue but for Greenland to become ice-free. So this is really something that is the eigendynamics, the self-dynamics of the Greenland ice sheet that leads to, once we cross this threshold, you can show also mathematically in this very simple approach like this, you can show that once you cross this critical threshold, then almost the entire ice mass is lost and Greenland declines to just a very small ice cap. And this has also been looked at with more complex numerical models. And there you also see that if you cross a critical temperature threshold, such as here, then you lose almost the entire Greenland ice sheet, leading to roughly 7 meters of global sea level rise. This warming threshold lies somewhere between 0.8 and 3.2 degrees of Celsius as of the latest estimates. Now, this is, of course, still a large range, but this also shows we're currently already within this range because we are at roughly 1 degree of global warming. And this is a simulation just showing what happens once you cross this critical threshold. So really, the Greenland ice sheet, this is just sort of the ice dynamics and the melting in itself. And due to this melt elevation feedback, almost the entire Greenland surface becomes ice-free. Now, of course, this doesn't happen overnight, but it takes a long time, thousands of years in this particular case. But it's very important to understand that there are these critical thresholds associated with ice dynamics, and we need to think of them because these long timescales actually also mean that we have to think of ice sheet mass balance and also sea level rise in terms of a commitment. Now, the story is very different for Antarctica. In Antarctica, it's much colder than in Greenland in general, so we have very little surface melting. But instead, we have a lot of these floating tongues, these floating ice shelves surrounding the Antarctic ice sheet, as you can see here. And that means that in Antarctica, the ice is in contact not just with the atmosphere, but also with the warmer ocean waters. And as you can see, the Antarctic ice sheet also has lost a lot of mass in the past decades in particular. And this was especially the case in West Antarctica, as you can see here. Mass loss has tripled just over the past 5 years, and this is associated with warmer ocean waters reaching the ice shelves and thereby also accelerating ice flow from the interior of the ice sheet. So this increase in mass loss has been largely driven by ice-ocean interactions. And the reason for this is, of course, the melting of ice shelves doesn't contribute to sea level rise directly, but the ice shelves act as a sort of a buffer or a plug. So if you decrease the ice thickness in the shelves, then you decrease that buffering effect, or the so-called buttressing effect, and that leads to an acceleration of ice flow from the interior, and that in turn leads to sea level rise. The question is, what is the overall impact on Antarctic ice flux and therefore also on the stability of Antarctica? And the reason why this has been in the news so much over the past years are these observations here from the Amundsen Basin in West Antarctica. What you see here is, first of all, over the past decades, these are the ice velocities, and you can see that the ice streams in this particular region have really accelerated quite strongly. So everything that's red and purple is an acceleration. And this goes along with a decrease in elevation. So the ice streams here have really retreated into the interior of the ice sheet and are now reaching places that are based much more deeper in the valley behind. Now, why is this of concern? This is again associated with a positive or self-reinforcing feedback mechanism. And the reason how this works is quite simple, actually. So here you have a sketch, a cut through West Antarctica, and there are two things that you can see that are true of most of the regions in West Antarctica. First of all, you have ice that's grounded below sea level, so these are the so-called marine ice sheets. And secondly, you can see that overall you have a decline in many regions of the bedrock slope. So that means the bedrock slope in the interior of the ice sheet is retrograde. So the ice, when it retreats, the grounding line, it will reach lower bedrock elevations. Now, this in turn can lead again to a positive feedback mechanism as follows. If you have a retreat of the grounding line to such a deeper region behind, then this means necessarily that the ice thickness in this region must be larger, because if it weren't, it would already be afloat in this area. A higher ice thickness, in turn, means that you probably have more ice flow across the grounding line, and that again leads to grounding line retreat. So you again have this positive feedback mechanism, and you can show in a cut like this in 2 dimensions that this must lead to an instability. This hypothesis of the marine ice sheet instability was already put forward in the 70s. What changed now is that these observations that we just saw over the past decades show that for these particular glaciers here in the Amundsen Basin in Western Antarctica, this critical threshold might already have been crossed. So the tipping point here might already have been crossed, and that means that the marine ice sheet instability might actually be underway in the Amundsen Basin in West Antarctica. This basin alone holds enough ice volume to raise global sea level by roughly 1 meter. The question that is still open is, well, how is this related to global warming, to man-made climate change? And the second question is, how fast will this actually happen? Because so far, what we know is mainly that there is this tipping point and that it has likely been crossed, but the question is how fast will the ice actually flow into the ocean? And because we don't live in a 2-dimensional world, but in a 3-dimensional world, this question becomes much more complex in a realistic case like this, because you have to take into account the buttressing effect of the ice shelves. What we can do with numerical ice flow models is study how, once this critical threshold is crossed, how the rest of the West Antarctic ice sheet might react to that. And this is what you see in this animation here. So this is from a simulation with the parallel ice sheet model. And everything that's been done here is really just triggering the instability in this particular region that you saw in the beginning. Everything else is kept constant, so there's no additional warming, there's no change in snowfall. And as you can see, through this feedback mechanism, through the marine ice sheet instability, once you destabilize this particular region, most of the marine ice sheet areas in West Antarctica follow. You can also see that ice sheets are very inert systems, so sea level rise actually takes thousands of years through this process. And I think that means as a lesson for us that we really need to start thinking about sea level rise in terms of commitment. This is just to show that not only in West Antarctica, but also in several basins in East Antarctica, these two conditions, that ice is grounded below sea level and you have a retrograde slope, that is actually fulfilled in several areas also in East Antarctica. And the potential in terms of sea level rise from all of these areas together is roughly 20 meters. And when we think about sea level commitment, we are, of course, not interested in global sea level rise, but we're interested in what's happening regionally to our coastlines. And this is what we've looked at here. So these are long-term sea level projections for a scenario of 1,280 gigatons of carbon release, which is still in accordance with the Paris Agreement. So we're staying just below 2 degrees in this scenario, and this is the long-term sea level rise. And what you see here in purple are all the areas that are heavily populated, so where today more than 50 million people are living, that might be underwater in the long-term future. So this concerns regions all along the American coastlines, but also in particular, for instance, Bangladesh would in this scenario actually lose a large part of its area. So I hope I could convince you that both the Greenland and the Antarctic ice sheet are truly tipping elements in the climate system. And as we all know from Tim's work and for instance, also John Schellenhuber's work, is that there are many other candidates in the climate system that also show this kind of critical threshold behavior and are therefore tipping elements in the climate system. And to these belong not only the cryosphere entities, but also large-scale circulations, like, for instance, the Atlantic thermohaline circulation, as well as large-scale biosphere components, such as the Amazon rainforest or also the coral reefs. And if we now go back to the very first slide of my talk, and we put this into context with the tipping elements here, here you see the Paris range of roughly 1.5 to 2 degrees of warming. And here you see, sort of from the current literature, all the different critical thresholds, what we know about them, including the uncertainty ranges for these different tipping elements. And as you can see, there are several tipping elements which are already at risk of transgressing that critical threshold within the Paris range. And to these belong the West Antarctic ice sheet, as well as Greenland, but also, for instance, the Arctic summer sea ice, the alpine glaciers, and the coral reefs. And what is still an open question is how these tipping elements interact and what this means for the overall stability of the Earth system. And when I say Earth system, there's, of course, a very important part missing. And this is what we've been discussing here at this conference, which is, of course, the Earth system is not just the climate system or the natural side of things, but people are actually living on the Earth system and are taking a huge effect on the Earth system as well. So we really need to start thinking of the Earth system as a whole Earth system, including humans as part of its agents. And I just want to raise the possibility that there might be feedback loops, including these natural tipping elements, as well as potential social or societal tipping elements. And this could, for instance, go as follows. So what we already observe is that people's attitude around the world is changing due to actually climate impacts, but also anticipation of potential future climate impacts. This might change to a lead in policy and behavior, and that in turn could help us reduce greenhouse gas emissions and thereby lead to a stabilization of this system. So I want to end with this note of hope that societal tipping might actually be a match for climate tipping, And we really need to start thinking about Earth system dynamics in this whole Earth kind of view. Thank you very much.
Thank you. You covered a lot of material. I'm just going to focus on one thing. Is within the Arctic, between 5,000 and 10,000 years ago, there was a lot of ice-free periods, and at the same time, it may or may not be related, that sea level was between 1 and 2 meters higher. So obviously a tipping point was not exceeded, but do you have any thoughts of what brought that condition back to where we, basically are today?
Yeah, so as for the Arctic and its sort of more recent history in Earth's history, we first of all need to distinguish between what's happening with the sea ice in the Arctic and what's going on in Greenland, of course. So mass loss from Greenland would actually contribute to sea level rise, whereas the sea ice conditions are just sort of a mediator in that particular, so with respect to sea level rise. But as you said, there have been a lot of changes observed, especially over the past thousands of years, even almost like a periodic change. And we also need to distinguish the overall response of the Arctic, especially summer sea ice, that is roughly linear. So the decrease in summer sea ice is actually roughly linear in comparison to the cumulative greenhouse gas emissions and therefore to warming. So this is not a tipping element, most likely with irreversibility, so with the hysteresis behavior, but it's rather a threshold behavior that is caused by just the cumulative greenhouse gas emissions. Whereas for the ice sheets, we really have these positive feedback mechanisms that lead to hysteresis. So the behavior is quite dissimilar.
One more question.
Thank you. So I just want to refer to a tipping point that you mentioned right at the very end. I think, to some extent, we're all stunned by the issues that you present in that presentation. So one tipping point that occurs to me that struck by your presentation was some of the graphics that you showed, some of the animations you showed, which really brought to life the challenges we're facing. To what extent can we, or are you using those graphics with the sort of, the popular rising in consciousness around this issue? And sort of related to that, to what extent do we have investigations that show how we might turn those animations around, if you like, those really striking animation you showed about the ice flow in Antarctica, for example. If we do manage to turn around the emissions curve, to what extent can we use those animations to illustrate what the hope might be?
So as for your first question, this really goes into the realm of climate communication and what these kinds of animations tell us about our current thinking and our understanding of the processes within the ice sheets and also other parts of the climate system. And I do think it's really important to be able to communicate this in terms that is very understandable to everyone. Because, as I said in the very beginning, I really think we all should care about ice sheets. They sometimes seem so far away. And what we're attempting to do is really show, well, this is very much connected to our everyday life as well. And the second point would be, well, this is clearly not the eternal ice. This is clearly not this ewig ice. But in fact, there are a lot of really drastic changes going on, especially in the past few decades. So maybe in a way, the ice sheets or the polar regions altogether can serve as a kind of an early warning system for us when it comes to climate change. And yeah, so that's for your first question. And the second question is, well, how far can we turn these around, and how far can we actually save parts of Antarctica or even reverse some of these changes? And I think the most important thing is we need to reduce greenhouse gas emissions and thereby avoid further global warming, because especially for Antarctica, you don't have just one tipping point, but you actually have different tipping points for all the different regions, the different ice basins in Antarctica. So if we want to avoid crossing further tipping points, then that necessarily means we need to reduce greenhouse gas emissions.
Thank you very much, Ricarda. That's,